Hello, today we're talking about geometric series. Now, the first page that you have is vocabulary, reminders of things that you've seen before, but I'm not going to go over this first page. You may need to take time and look over this page. Any formulas you see, you must memorize. So again, if you want to pause the video now and go ahead and read over this, that might be helpful. But this first page is going to be left up to you to complete. So moving on to the next page. Exploration 12-2B, Review of Geometric Series. So number one, from algebra and pre-calculus courses, you recall that a geometric series, again from the front, is a series for which the next term is formed by blank, the previous term by a blank called the blank blank. What words go in the blanks? So for the first blank, I'm going to call that one green. It's a series for which the next term is formed by multiplying the previous term by a constant, multiplied by a constant, and this constant has a name, and it is called the common ratio. So that's the definition of a geometric series. So for number two, for the geometric series, 1000 plus 900 plus blah, 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 write the next three terms. So to find my common ratio, that's going to be the second term divided by the first term, or you can choose any two consecutive terms, but take the furthest one away goes on top, and then the closest to the beginning term goes on the bottom. So this common ratio is 9 over 10. And so to find term 3, that's going to be 900 times 9 over 10. And that comes out to be 8100 divided by 10, which is 810. So that's term 3. So then term 4 is, again, take that number, multiply it by 9 over 10, and that comes out to be 729. And term 4, we take that number, 729, and we're going to multiply it by 9 over 10, and we're starting to get our decimals now, 656.1. So again, we just multiply by the common ratio to get each of the terms. Number 3, what is the common ratio equal for the series in problem 2? And that was 9 over 10. So in number 4, rewrite your answers to problem 2 so that they are expressed as 1,000 times a power of the common ratio. So it's saying we want 1,000 times 9 over 10 raised to a power. Now our term number 1 was 1,000. We knew that. That was given to us up in question 2. So I really need this to end up being 1,000, so my common ratio doesn't need to be multiplied by this. I need to multiply 1,000 by 1, which means the exponent for that first term has to be 0. Now for term 2, we know that that was 900. So that's going to be 1,000 times 9 over 10, and that's going to be raised to the first. So if I take 1,000, multiply it by my common ratio, I'm going to get 900. Next term that we found was 810, and that's going to be 1,000. I think you can see the pattern at this point of 910 raised to the second power. Then we are to 1,000 times 9 over 10 raised to the third power, and the last one is 1,000 times 9 over 10 raised to the fourth power. Why are we doing this? Let's see. Okay, number 5, use that pattern to evaluate the 50th term. So for the 50th term, it's going to be 1,000 times 9 over 10, but what power am I going to raise it to? Well, let's look back at these terms that I've already done. In T1, the exponent was 0, but I was on term number 1. In T2, the exponent was 1, but I was on term number 2. In T3, the exponent was 2, but I was on term number 3. Exponent 3, term 4, exponent 4, term 5, which means all I'm really doing is taking whichever term I'm on, which I'm on the 50th term, and I'm subtracting 1 to get this exponent. So in number 6, it says, okay, great, just give me the general formula for this now. So T sub n, you tell me which term number you want. It's going to be 1,000 times 9 over 10 raised to the n minus 1. Now, they also said we don't really want those numbers in there. This is for the one we just worked on. So the general formula for any geometric series is going to be T sub n is going to be that first term. That's really where that 1,000 came from. That's my first term, times my common ratio raised to n minus 1. So that's going to be our formula for any geometric series. Number 7. Write the formula in problem 6 again verbally. Okay, so all we do is we take the first term times the common ratio raised to 1 less than the term number. And if you need a minute to write that down, go ahead and pause the video. Find the limit as n approaches infinity for the series in problem 2. So now we are specifically talking about this series. This is our series number 2. And now we're going to do the limit as n approaches infinity of this. So what we need to know is, well, what's happening as my 9/10 is being raised to bigger and bigger and bigger powers? Well, anytime that we have a fractional value raised to an infinity, basically, so we're looking like this, 1,000 raised times 9 to the 10, 9 over 10 raised to the infinity, that thing is trying to become 0. Now, let's think for a minute, go back to our table at the beginning. What was happening, sorry, in number 2, what was happening to each of my t values? I started at 1,000, and I went down to 900, I went down to 810, I went down to 729, I went down to finally 656.1. So each of these terms is going down. So what this is saying is, what's eventually going to happen to these terms if I keep having higher and higher term numbers? So basically that's going to be 1,000 times 0, which is 0. So my terms are eventually going to go to 0. Well, they're trying to get to 0. Number 9. A series has an infinite number of terms, so you can't add all of them. So does that make sense? Series goes on forever unless you've been given a specific beginning and a specific ending. But you can add part of them. Find the fifth partial sum, we will call that S sub 5, of the geometric series in problem 2. So what S sub 5 means is I'm going to add, so I'll write it up here, T1 plus T2 plus T3 plus T4 plus T5? No, plus T4. 1, 2, 3, 4, 5. Oh, I'm sorry. I'm looking at my work over here, and I apologize. I mislabeled my blue in number 2. I labeled it as T4, so please make sure yours does not say T4. Yours should say T5. I apologize. Okay, so for the sum, partial sum, the fifth partial sum, S sub 5, we're going to add the first 5 terms. So in our case, that's going to be 1,000 plus 900 plus 810 plus 729 plus 6.1, excuse me. And when we add that all up, we get 4,095 0.1. And again, we're just adding those up. Number 10, the fifth partial sum of a geometric series can be written as this. So what this is saying is take the first term, add it to the first term, which was 1,000, times my common ratio raised to the first power. Then I take my first term, multiply it by the common ratio raised to the second power. First term, common ratio raised to the third power. First term, common ratio raised to the fourth power. And add those all up. That's the same thing. It's just saying, well, that's exactly what we're doing here. So we're going to do some algebra to that. So it says multiply both sides of this equation by r. So I have r times s sub 5 equals t1 times r plus t1 times r cubed squared, plus t1 times r cubed plus t1 times r the fourth. How many terms do I have? 1, 2, 3, 4. Plus t1 times r to the fifth. So I end up with this when I multiply through by r. Then subtract to find s sub 5 minus r s sub 5. So I am now going to subtract my s sub 5. But I have my s sub 5 is this. Now I'm not going to fit this all in one line, so I apologize. I'm going to end up wrapping this around. So I'm going to take s sub 5 and subtract my r times s sub 5. I don't know why I used a 5, because my 5s look like s's. So I'm going to take s sub 5, which is this thing right here. So t sub 1 plus t sub 1 r plus t sub 1 r squared plus t sub 1 r cubed plus t sub 1 r to the fourth. And I'm going to subtract, again, this is a continuation, what I already had there, which is this part. So t sub 1 r plus t sub 1 r squared plus t sub 1 r cubed plus t sub 1 r the fourth plus t sub 1 r the fifth. And then we're going to simplify this. So if we were to simplify, I'm going to use my red, because basically I have everything positive and I'm subtracting away the parentheses. So I should just be able to cancel terms out. So you see I have a t sub 1 r here and a t sub 1 r here. Great. Those are going to subtract out. I have a t sub 1 r squared and a t sub 1 r squared. Those are going to cancel out. I have a t sub 1 r cubed and a t sub 1 r cubed. Those will cancel out. My t sub 1 r the fourth will cancel out. So I'm left with s sub 5. Trying to make my s's and my 5s look different. Minus r times s sub 5 equals t sub 1 minus, don't forget you're distributing that negative, t sub 1 r to the fifth. So that's all we had to do for number 10, which is good because we have run out of room. So number 11, by appropriate algebra, find a closed formula for s sub 5 in terms of t1 multiplied by a fraction containing r and 5. Oh goodness. Okay, so let's look back at the blue statement that I have. I'm trying to solve for s sub 5. You see that I can factor out an s sub 5 on the left side of the equation by GCF. So if I factor out my s sub 5, I am left with 1 minus r. And again, if you were to distribute that blue s sub 5 to the 1 minus r, you should get what we had right here. That's what I was trying to write after factoring out the s sub 5. So this is equal to t sub 1 minus t sub 1 r5. You know what? I'm going to change that. I'm going to go ahead. I'm going to go ahead and factor my t sub 1 out because I was asked to put that in terms of t1 multiplied by a fraction. So I'm going to pull my t sub 1 out just like I pulled out my s sub 5, 1 minus r to the fifth power. So I'm still trying to get s sub 5 to be alone. So I have s sub 5, and now I'm going to divide by the red 1 minus r. And because of the way they had it written, we want t sub 1 times a fraction. So I would just clean this up a little bit. to write it the way it was asked to be written, d sub 1 times 1 minus r to the 5th divided by 1 minus r, and close my parentheses. So apparently what I have is I have a formula now for the 5th partial sum of a series. So number 12 is saying, well, why don't you test it out in problem 11 by calculating s sub 7 for the series in problem 2, then do it by calculating term by term, adding them up. So we're going to go ahead and do that. Hopefully I have enough room to write. So first thing that I want to do is test my formula. So according to my formula, s sub 7 is going to be the first term times 1 minus, let's go ahead and fill stuff in, sorry. We know the first term is 1,000. We know what our r is. So 1,000, my first term, times 1 minus 9 over 10 raised to the 7th power over 1 minus 9 over 10. So we're going to pick up our calculator and we're going to work that out. So go ahead, get your calculator, work this thing out. I got 5217.031. Sorry, I think I lost a decimal place when I wrote my answers down. So this is that sum. Again, put 4 decimal places if you have it. So now the next thing is, well, let's figure out what we would get if we added the first 7 terms. Well, I'm going to remind ourselves that we actually have the 5th partial sum. I'm going to scroll up and grab it because I don't remember it. We have our partial sum is at the top, 4095.1. And so what we need to do is we need to find the next 2 terms. So the next term is going to be, hold on again, I'm scrolling back up to find, term number 5 was 656.1. So I need to take 656.1 times 9 over 10. So let's figure out what that is. And I got that to be 590.49. And then I need to add, so that would be the 6th term that I have in blue. And in black, we'll have the next term, the 7th term. And that's going to be 590.49 times 9 over 10 again. And when you calculate that out, we get 531.441. So ultimately, what we want to do is we want to add our 5th partial sum, which we had already calculated, plus the next 2 terms, 590.49 plus 531.441, add those up, and I get the same thing, 5,217.031, which is what I wanted. So number 13, use the formula in problem 11 to find the partial sum as n approaches infinity. Okay, now this partial sum is not the same as number 8, which was the single term. Now in number 8, we know that each term is getting smaller and smaller and smaller and smaller, and eventually the terms are trying to become 0. Number 13, it wants to know, well, what's the actual sum trying to go towards? Because that's not going to be going towards 0. So we're going to find our limit as n approaches infinity of 1,000 times 1 minus 9 over 10 raised to the n over 1 minus 9 over 10. So from here, we can work this out. 1 minus 9 over 10 is going to be 1 over 10. So this is my limit as n approaches infinity of 1,000 times 1 minus 9 over 10 to the n all over 1/10, which really means we have the limit as n approaches infinity of 10,000. We multiply by the 10 times 1 minus 9 over 10 to the n. And as n is approaching infinity, that 9/10 raised to the n is going to 0, which means we have 10,000 times 1 minus 0, which is 10,000. So my partial sum is approaching 10,000. There you go, a little recap of geometric series. Please bring any questions you have to class, and I hope you have a wonderful evening.